In this section, we're going to talk about areas between curves. Now, the last few sections, we've really been developing the concept of the definite integral and practicing and getting more comfortable with that. But now we're going to expand the idea of the definite integral to more complex areas. And we're going to focus on three big topics when finding areas between curves. The first topic is going to be really simple, where one function is completely above the other on the interval that we're trying to find that area. Then the next topic we're going to talk about is when it gets more complex and the two functions cross each other and we have to break it up into separate regions. And then the third situation that we're going to talk about is when we have to integrate with respect to y. So the whole idea of finding the area between two curves is basically just extending our concept of the definite integral that we have already. And if you notice, f of x in this picture is above g of x. So when you look at the picture labeled A, we're just going to be dividing them up into rectangles again. But the thing that's different about this is that in order to find the height of the rectangle, we need to take the height of f of x and subtract the height of g of x to find the height of the rectangle between the areas. So when we write the Riemann sums for finding the area between curves, we're going to write this as A is equal to the limit as n approaches infinity. The Riemann sums I is equal to 1 to n. And we're going to find the difference in the heights of the functions to find the height of the rectangle. So this would give us the height of the rectangle that's between the two curves. And then, of course, the width of the rectangle does not change. Now, rather than go through this process the long way, we know that we can just use a definite integral to do this. So if we use a definite integral to do this, we're going to find the area between the two curves by finding the area on the interval from A to B by taking the area under the curve of f of x and then subtracting the area under the curve of g of x. And what's left is going to be the area between them. So this is the trick that we're going to use so that we don't have to go through all the rectangles and the limit of the Riemann sums. And so the formal definition is down here. But in order for this to work, f of x needs to be completely above g of x on that interval that we are finding the area of. So this is key for this integral. Let's walk through the first example. It says, if R is the region bounded above by the graph of f of x is equal to x plus 4, and below by the graph of the function 3 minus x over 2 over the interval from 1 to 4, we're going to find the region of R. So in blue, f of x is x plus 4, that's above. And then g of x is in orange below, which is 3 minus x over 2. And between the x values 1 and 4, we want to find this area. So we're going to set up the area using that theorem to find that area. We're going to write it from 1 to 4, and we're going to take the upper function, which is f of x. You always want to take the upper function and subtract the lower function. So the function that is above is x plus 4, and you want to subtract g of x because that's below. And I would really recommend that you put this in parentheses when you set it up, because a lot of times people forget to distribute the negative. We're going to subtract 3 minus x over 2 and dx. When I simplify this, it always makes it a lot easier to find the integral when you simplify first if you can. When I combine these terms and clean it up, I'm going to get the integral of 3x over 2 plus 1 dx. I'm going to find the antiderivative of 3x over 2 first. So I'm going to increase the exponent for x by 1 and then divide by that. So I have 3/2 x squared over 2 plus, now the antiderivative for 1 is just x. I could put the plus c in there, but since we know that it's going to get subtracted out since we're working a definite integral, I'm just going to leave that out. And I'm going to evaluate this from 1 to 4. I'm going to go ahead and evaluate it 4 first. Since I have 2 2's in the denominator, that's 3/4. And when I plug in the 4, I get 16, 4 squared. Then plus 4. Now I'm going to subtract what I get when I plug in 1. So I have 3/4 times 1 plus 1. Now when I work out what's in this first bracket, I'm going to get 16. When I work out what's in the second bracket, that's going to give me, let's see, 4 over 4, 7/4. And when I do that last bit of arithmetic, we're going to get 57 over 4. Now, since we're finding the area under this curve, this is going to be units squared. They didn't give us what the units were, so we're just... In this next example, we're going to find the area of the region that's bounded between two curves. It says if R is the region bounded above by the graph of the function 9 minus x over 2 squared and below by the graph of the function 6 minus x, we want to find the area of region R. So we're trying to find this shaded area here. Now, the first thing I would do is, because we don't know what our upper and lower limits are, we don't know exactly what interval this is on, the problem doesn't tell us. So we need to figure out where our intersection points are so we can see what our upper and lower limits are going to be. So the first thing we need to do is set these two equations equal to each other and find where they intersect. So I'm going to set f of x equal to g of x and find those values of x where their y values are the same. So we have 9 minus x over 2 squared is equal to 6 minus x. I'm going to simplify this x over 2 squared and write it as x squared over 4. I think what I'm going to do next, since I prefer working without fractions, is clear out that fraction of 1/4. That's more of a preference. If you don't mind working with fractions, you can leave that in. I'm going to go ahead and clear everything by multiplying every term by 4. So that's going to give me a 36 minus x squared is equal to 24 minus 4x. Now, what we have here is a quadratic to solve because I have an x squared. That's my highest exponent. It's a squared, so I know this is a quadratic. So we have factoring, we have quadratic formula, we have complete the square. We have all kinds of methods to use to solve this quadratic. I prefer to try to factor if I can first. You can use another method if you'd like. So since I'm going to try to solve this by factoring, I'm going to move everything to one side and set it equal to 0. So that means we're going to get x squared minus 4x minus 12 is equal to 0. Then we can try to factor that. Does that factor? Yeah, that factors into x minus 6, x plus 2. So when I solve this, I get x is 6 and x is negative 2. So those should be the two places where we have our intersection points. And according to the graph, that looks reasonable. So now I know what my upper and lower bounds should be. So I know I'm going to integrate from -2 to 6 on that interval. Now, when I set up my integral, remember you always want to put the function that's on top first. So I'm going to write this as 9 minus x squared over 4 minus 6 minus x dx. When we simplify that and combine like terms, we're going to get 3 minus x squared over 4 plus x dx. Now, when I go ahead and find the antiderivative of 3 is 3x. The antiderivative of x squared over 4 is going to be x to the third over 3 times 1/4, which I can rewrite that since I have a 4 and the 3 in the denominator. I'm going to rewrite that as 1/12 x to the third. When I find the antiderivative of x, that's going to give me x squared over 2. And I'm going to evaluate this from -6 to 2. Since we're getting pretty comfortable with this and we've done this enough times, I'm going to let you guys do that work. Just check to make sure that you get the same answer as me. You should get 64 over 3. So now we're going to talk about what's called area of compound regions. And we're going to take what we've learned so far and apply it to more complicated areas. The first couple of examples we went through, when we looked at the entire interval of interest, one function was always above the other function. Now what we're going to look at is if we're looking at the entire interval of interest, what do we do if one function crosses the other? So for example, if I have one function that looks like this, and then another function that looks like this, and we want to look at the entire interval from 0 to say b, if you notice on that interval, I'll call the pink function p, and I'll call the green function g. If you notice on that entire interval from 0 to b that we're interested in, not one function is not always above the other because they cross. So in order to use that same method we used in the previous examples, one function always has to be above the other. Now if I call this where they intersect A, what we can do to handle this situation is just break it up into two integrals. So I can say the integral from 0 to b can be written as the integral from 0 to a plus the integral from a to b. That way, if we split it up, the integral from 0 to a always has the green function above the pink function. And then when we look at the interval from a to b, the pink function is always above the green function. And then we can just find those areas separately and add them up. The theorem writes it mathematically as what we're doing is we're finding the integral of the absolute value of f of x minus g of x, which is mathematically correct, but in practice, what we're really doing is just breaking the area up into smaller chunks and adding them together in order to make sure that one function on that interval is above the other function at all. Okay, now we're going to actually apply that idea to an example. We are going to look at the graphs of the function f of x is equal to sine x and g of x is equal to cosine x over the interval from 0 to pi. Now, that gives us the shaded blue area in the picture, but notice on the first interval, where I separated the intervals with my dashed lines, on the first interval, when we're looking at that shaded area, cosine is above sine, and then in the second interval, sine is above cosine. So what we need to do is we need to find that intersection point So we know how to break up this interval and write them as separate integrals. Now, you can use a graphing calculator. You can set the two equations equal to each other and solve. No matter how you want to do it, when we find that intersection point, we're going to get that x is equal to pi over 4. So when I want to find the entire interval from 0 to pi of f of x minus g of x inside my absolute values, we can write that as two separate intervals from 0 to pi over 4. I'm going to call that, I'll highlight that in green here. That will be my area 1 in green. Let me use a different color in purple to find that second area. I'll call that area 2. We're going to have a different integral. So when we're trying to find that green area, that first area, cosine is above sine of x. So I'm going to write cosine x first minus sine of x dx plus, and then I'm going to find the rest of the interval from pi over 4 to pi. That's the purple area, area 2. On that area, sine of x is above cosine of x. So I'm going to write sine of x first minus cosine of x dx. So now when I find area 1, I'm going to integrate that first integral. So the antiderivative of cosine is sine minus the antiderivative of sine is negative cosine. So I'm going to have a double negative, which means this is going to be a positive, and I'm going to integrate that on 0 to pi over 4. So that gives me the area in green. Now when I do the second integral, the antiderivative of sine is negative cosine, and I subtract the antiderivative of cosine, which is sine. I'm going to evaluate that from pi over 4 to pi, and that will give me my second area in purple. When I plug in pi over 4, I'm going to get the square root of 2 over 2 plus the square root of 2 over 2. Then I go to subtract what I get when I plug in 0. When I plug in 0, I get 0 plus 1. When I evaluate area 2, when I plug in pi, I'm going to get negative 1, but that negative in front of the cosine is going to make it positive 1. When I plug in pi for sine, that gives me 0. Now, when I plug in pi over 4, I'm going to get negative square root of 2 over 2 minus square root of 2 over 2. Now, when I clean all this up, area 1 is going to give me square root of 2 minus 1. When I clean up all this, I'm going to get 1 plus the square root of 2. And then when I combine all that together, I get my final answer is 2 square roots of 2. So looking back up here, the green area plus the purple area together is going to give me an area of 2 square roots of 2 units squared. Okay, let's walk through one more example so that we can practice of having to split up the integrals. If we look at this picture, we have the graph of x squared, and we have the graph of 2 minus x, and we want to find that blue shaded region labeled R. But if you notice, we have to split this up into two intervals because on the interval from 0 to 1, 2 minus x is above the graph, x squared. And then when we look at the interval from 1 to 2, x squared is above 2 minus x. So they get swapped. So we have to split this up again into two pieces. Now, the nice thing about looking at this picture is that we can see where the intersection point is, so we don't have to actually go through the steps of finding that. So we're going to split this up into two regions and add those areas together. I'm going to split it up into the green region and the pink region. So we're going to find the green region first. So from 0 to 1. Now for that area, we really just need to find the area under the curve of x squared. We're not looking at this area in orange where it's between the two functions. If it was between the two functions, then I would have to take 2 minus x and subtract x squared. But since we're trying to find the green region, which is just strictly below x squared, bounded by the x-axis, I'm just finding the integral from 0 to 1 of x squared dx. So I'm going to label this as the first area in green. Then I want to add the second area, which would give me the pink area, and that's going from 1 to 2. And that is actually the same situation, but with the function 2 minus x. I'm not finding the area between the two curves, x squared and 2 minus x. If we were doing that, then I would be looking for this orange area between the two curves. What I'm really doing is I'm looking for the area under the curve bounded by the x-axis of that function 2 minus x. So I'm just going to write it as the integral from 1 to 2 of 2 minus x dx. That will give me the pink area. So now I have to integrate this and then evaluate on each of the intervals. If I take the antiderivative of x squared, that's x to the third over 3, and I need to evaluate that from 0 to 1, that's going to give me the green area. I'm going to keep trying to color code this for you and label it. And then I want to evaluate the integral 2 minus x from 1 to 2. So the antiderivative of 2 is 2x. And then the antiderivative of minus x is minus x squared over 2. And I want to evaluate that on the interval 1 to 2. So now when I go ahead and evaluate that, I'm going to plug in 1 first. So I get 1/3. When I plug in 0, I get minus 0. So that gives me area 1. Then I'm going to add that to what I get when I evaluate the second area from 1 to 2. So when I plug in 2, I get 4 minus 2. And I'm going to subtract what I get when I plug in 1. That's 2 minus 1/2. That's going to give me area 2, which is the pink area. So 1/3 minus 0, that's going to give me 1/3. When I clean up what's in the brackets for the second area, I'm going to get 1/2. And when I add the two areas together for the total area, that's going to give me 5/6. So the total area is going to be 5/6, and then generically we're going to write unix squared. Now, the last topic we're going to go over is how to integrate with respect to y if we want to look at a region in terms of y instead of x. So basically that's going to happen when we want to look at, instead of drawing our rectangles vertically and adding them all up vertically and doing our widths with respect to x, if we want to make our rectangles going sideways and finding those areas, so now our widths are going to be with respect to y. So here's some pictures here to kind of visualize what we mean by that. So if I wanted to find the area in graph A without having to break it up separate integrals, what I can do is just change my rectangles to go horizontal instead of vertical and just do it with respect to y instead. And the only thing that we need to do to change things up is to just solve the equation for x and have the equation as x with respect to y. So here's officially what we're going to do. That's the mathematical way to write this. But in reality, what we're doing is we're just making our rectangle sideways. So let's walk through this example. This is the example that we just went over when we broke it up into two areas, right? When we did this example, we had the green area here, and then we had the pink area here, and we split it up into two separate areas. And when we did that, we got a total area of 5/6 units squared. Now we're going to use a different method and show you how we can get the same answer, but we're going to do it in one integral with respect to y. So now we're going to imagine that our rectangles are going across this way. If you turn your page 90 degrees to the left, we're imagining now that 2 minus x is going to be our upper limit, and x squared is going to be our lower limit if we rotate our picture 90 degrees to the left. But in order to do that, we need to solve each of these equations for y and plug it in that way. So the first thing we need to do is express the graphs as a function of y. So we have f of x is equal to x squared. I'm going to rewrite it as y is equal to x squared. When I solve this for x, I'm going to get x is equal to the square root of y. Now for my second function, I have g of x is equal to 2 minus x. I'm going to rewrite that as y is equal to 2 minus x. And when I solve that for x, I'm going to get that x is equal to 2 minus y. So now I have my functions written as x with respect to y. So now I'm going to write my integral as my upper function as being 2 minus y. And I'm going to subtract my lower function, which is the square root of y. And I'm going to do this with respect to y. Now, don't forget, we're looking at it as if we're tilting the page 90 degrees to the left. So 2 minus x is going to be my upper function. And I'm going to subtract my lower function, which is x squared. Now, we need to check our intervals. If we're doing this with respect to y instead of x, when we were doing it with respect to x, we were on the interval from 0 to 2. Now that we're doing it with respect to y, we're doing it on this interval from 0 to 1. So now my upper and lower limits are going to be 0 to 1. So when I find the antiderivative of this, I'm going to have 2y minus y squared over 2 minus 2/3 y to the 3/2, because remember the square root of y is y to the 1/2. So I have to add 1 to the 1/2 power and divide by 3/2, which is the same as multiplying by 2/3. And now we're going to evaluate that from 0 to 1. So when I plug in 1, I get 2 times 1 minus 1/2 minus 2/3. And then when I subtract what I get when I plug in 0, that's going to give me 0. And when I take 2 minus 1/2 minus 2/3, I'm going to get 5/6, which is the same as what we got when we did it the previous method by breaking it up into two separate integrals. We should get the same answer because it's the same area. We're just going about it in a different way.